right, so imagine that I throw this problem at you, right? And you're talking to some state senator or something like that, or whatever, and they say, the average teacher makes $50,000 a year in pay. And this includes all of the, extra work that teachers do. So they sometimes get stipends for doing summer work or whatever else they get paid to do. So this is what they're saying. Average is $50,000. So we want to test that this claim is not true at a 5% level of significance, or alpha is 0.05, by sampling 16 teachers, getting their average pay of $51,000, and the standard deviation is 3,000. All right? So when you're testing a claim, folks, first step, get your hoe and your ha. All right?
Did you mean this was a 10?
Yeah, that's what I was wondering.
Yeah.
Oh,
I'm like 9.2. Didn't we already go over that?
10. Whatever chapter we're on. Chapter 9 would have just said, what's the confidence interval for that? Alright, so what's the null hypothesis and the alternative hypothesis for this problem?
What was the 50,000 implies that it's how is that it's 50 that equals 50,000?
Okay, good. So the hoe is that mu equals the $50,000, right? Now what's the opposite of equal to?
Not
Not
equal.
Okay, good. So the ha, or what we're trying to prove, is that the average teacher salary is not $50,000. It's something else entirely. All right? Now please remember, when you're dealing with equals and not equals, that your test is a two-tailed test. When it is less than or greater than, that's when you're dealing with a one-tailed test. All right? So keep track of those two sorts of things. So we've got the ho and the ha set up. Now, remember that we can reject the ho if t is less than our critical value, alpha. If negative t is less than our negative alpha over 2, or t is greater than t sub alpha over 2. Okay? And why is it alpha over 2?
The different ends of the tail.
Yeah, because it's two-tailed, right? You do the alpha over 2 when you have a two-tailed test. The equal to, not equal to. If it was just one-sided, then it would be just either the one side less than negatives or the other side greater than positives, where the alpha was not divided by 2. All right, so now how do we calculate our t statistic in this particular case? First off, what's our t sub alpha over 2? What do we look up? Get out your tables, your t tables. So use table C. And again, be careful, folks. The alpha over 2, either way you look at it, just be careful. You can either use 0.05 two tails or 0.025 one tail. You'll note that those are both the exact same column, okay? Right there in the middle.
1 or 2.131.
What are my degrees of freedom?
15.
Okay, good. .131. So now, if our t statistic is either more than this or less than the negative of this, we get to reject, right? Either side. Now, to calculate our t statistic, remember that we're going to take x bar minus mu all over S over the square root of n. What's x bar? What was my sample average? That's the 51,000. The mu, remember the mu always comes from the ho and the ha, okay, folks? Minus the 50,000. And what are we going to divide by? 3,000 over the square root of 16. Calculator problem, crank it out. And again, folks, you're more than welcome to do some of this stuff in your head. Hopefully you can look at the square root of 16 and go, hey, wait a second. I know what that is. It be faux. Again, be careful. Okay. Everybody get 1.3333? So, is my t value greater than my t sub alpha over 2 value? No. Is t greater than t sub alpha over 2? And note, I did greater than because my t value is positive. If the t value had been negative, I would have done the whole negative side of it, which hopefully makes sense. Key here is that it is not, no. Therefore, we cannot reject the null hypothesis. Again, note, we are not validating the null hypothesis. We are not proving that the average teacher salary is 50,000 by doing this. We are just not able to disprove it. That's it. All right? So just because you reject the hoe doesn't mean that you don't actually visit the hoe. And I mean that in the null hypothesis kind of way. What happens in Vegas stays in Vegas, especially if you take the right medicine. And I'm just kidding, of course. All right, so not bad. All right, so I wanted to make sure we did one example where we didn't reject. So there. Here's one that it didn't work, so we're not going to reject the null hypothesis. And again, this. Just give me this at the end, because the idea here is that you can either reject it or you can not reject it. All right? Right. All right, so. Technically, it all has to be equal to 30. So, when you have a small sample size, folks, you have to use t-scores. When you have a large sample size, instead of using t, it's easier than that. Z-scores. Yeah, the easier ones, yes. Z-scores are generally easier to deal with. Again, though, you still have to be a little bit careful dealing with the one-tailed versus two-tailed tests. So please be careful. cool thing is that otherwise, it's basically the same as 10.2, okay? So the same concept of if you're doing more than, you're going to have a one-tailed test on the right. If you're doing less than, you're going to have a one-tailed test on the left. If you have a not equals to, then it's a two-tailed test. And the cool thing about it is that z is going to be calculated exactly the same way that t is. X bar minus mu all over s over the square root of n. It's almost a carbon copy, okay? Which is relatively nice. All right, so let's try a sample problem. All right, so suppose you hear that the average BTC student goes to school for 3 years. You think the average is higher, right? So you hear that it's 3, but you want to believe that it's really higher, okay? So test at let's test at say the test at alpha equals the 0.01 level, or a 1% level of significance. When we sample 100 BTC students, and the average time in school is 3.1 years. Number of years they're in school. The average. So I asked 100 people, right? Some of them was 3, some of them was 4, some of them was 2, some of them was 5. The average worked about out to be 3.1. And the standard deviation equaled a half a year. Well, no, again, it's the average of 100 people. So everybody gave a whole numbered answer, but when you averaged out the 100 people, it averaged out to 3.1. All right, so what's the first thing that we do when we're testing things? O and hop. So what is our null hypothesis and our alternative hypothesis? Now, what am I specifically trying to test, though?
Less than or equal to 3.
Because what am I testing? What do I want to believe is true? Yeah, I want it to be more than 3 years, okay? So if you're trying to test for a specific value, that is your hop, all right? And so the ho, the assumption, or the assumed value, essentially we're still following the same sort of thing, right? It's less than or equal to 3, right? And that still essentially follows what the assumption was at the beginning, that the student goes to school for 3 years on average. Less than or equal to 3 can be the same as 3 to some degree. And the idea here is, of course, that I wanted you to do a one-tailed test in this example. Okay, that's why I did the more than. All right? So, this is a one-tailed test. And note that we're looking for values that are greater than, so we want to reject if z is greater than whatever our critical value of z is going to be. All right, so first off, what is our z critical at alpha equals 0.01? Now be a little bit cautious. The critical values in that table on table B at the bottom, those are only for two-tailed tests, okay? So you need to somehow look at this table and give me the value for this as if it were a one-tailed test, all right? So using table B at the bottom, the little z critical values, okay? So in theory, folks, I want this to be 1%, 0.01. The area over on the far right-hand side is 0.01.
2.326.
Which one are you using?
I went to table C and used 0.01 for one tail with infinite degrees of freedom.
Use table B. Don't use the table C tables. It's okay. You can use those. It's essentially the same thing. But in theory, you should really use the table B values along the bottom.
Are you talking like actually in the table?
No, the special values, the
Oh,
critical
okay.
values
So we
along the
just-
bottom, right?
So we just take the 0.98 for two tails.
Yes, we use the 0.98 value because for two tails, you have 1% here and 1% there. Therefore, this is going to be the 98% side as opposed to the 99% side. It looks a little bit weird, but that's why it works. So this value over here is really 2.33. Because in theory, if I have the other end, this would be negative 2.33. If this would be 0.01, the area in between would be the 0.98. All right? So our z critical value for alpha equals 0.01, one-tailed, is 2.33. Although I like the thought of trying to use the t-table at the infinite level. So now, does everybody see why we use 2.33 instead of 2.575? Right, because it looks like that's what we should use, but that would be only if this were a two-tail test, and since this is a one-tail test, that's why we use the 0.98. All right? Your actual z value that you're calculating, folks, that's the same stuff. X bar minus mu all over s over the square root of n. So what was my x bar? 3.1 minus 3.0 all divided by 0.5 over the square root of 100. something like that. 2. Note, is our z greater than our z critical? It's less than, so we can't reject. Our z is not greater than z crit, so we cannot reject our null hypothesis. So we would like to say that students stay here longer than 3 years on average, but based on our data, we cannot confirm it. All right? At least not at a 0.01 level of significance. All right. Not too bad? All right, so which ones did I assign in 10.3?
8, 10, 12, 16, 18, 20, 26, 28.
I got a little carried away, huh?
So you're saying you want to cut half of that, right?
A lot of those are just a matter of you reading some values and saying, hey, is this true or is this not true? So some of those are not requiring a whole lot of calculation.
I can dig that.
All right, now, before we move on, okay? So there's a minor value that we can work with in here. So when you get to work with z-scores, folks, a standard parameter that people calculate we can use our z-value to determine a p-score for our sample. So a p-score, folks, and this is just something that if you ever get into the statistical world, invariably you will have people who will talk to you about p-scores. It is just a part of life. Honestly, when I learned about these the first time I went through a statistics class, I sort of thought they were silly because I'm like, we have what we're looking for. You know how to reject these particular things, but very few statisticians actually use the sort of traditional is z less than a z critical value. Instead, what they tend to do is to calculate a z-score, a z-value, and then when they get the z-value, they look at what the p-score for that z-value is. Now, what the p-score is basically just looking up whatever the z-score is in table A or B of our original tables. So in other words, look up, let's see, negative 2.00, right? Look up z equals, and note we use the negative because that gives us the smaller value inside of our z tables. So what is the percentage for z equal negative 2? What was it? 0.0228. And the idea here, folks, is that this p-score is telling us what level of significance our data is at. Okay? So our data is at basically 0.0228 level of significance. Is that within our 0.01 level of significance? In other words, is it less than our alpha? Is 0.0228 less than 0.01? No. This is another reason that you will reject or not reject the null hypothesis. Okay? If the p-score is less than alpha, you reject the null hypothesis. If it's not less than alpha, you cannot reject the null hypothesis. It's exactly the same thing as doing if your z-score is greater than your z-critical value. It's the exact same thing.
We can reject or we can't?
We cannot reject. Oh, sorry, yeah. Oh no, if it's less than, we can reject. If it's
Okay.
greater than, then we cannot. And since ours is greater than, we cannot reject. Or if the p-score is greater than alpha, you cannot reject the null hypothesis. And so a lot of times you will deal with p-scores instead of dealing with z-critical scores, just because that's essentially the statistic that more research scientists have been using to drive whether or not they accept or reject whatever the hypothesis are claiming. Why? Honestly, I don't know. It's no different than looking z to z-crit versus p to to alpha. It's just another way of looking at it. Again, what I assume is that when you start talking p-scores, you start to sound sort of more official or more statistician-y, and so that's why we do it. Honestly, I swear to God, I don't know. I really don't know. But when I first learned this, like I said, I never even bothered with p-scores. But when I got out into the real world and started listening to people talk about statistical analysis, they would always talk about p-scores. And for about 3 or 4 months, I had no idea what the hell they were even talking about, because I didn't even remember that we had done this back when I did it my first time. And so I had to go back and re-research it and said, oh, it's the same as what I was doing with this z and z-critical, but it's just using the opposite side of it, right? Is looking at the p-score and the alpha instead of the z and the z-critical. I'm assuming it's because they don't want to have to look up z-critical values and they can just compare the p-score to the alpha and then they're done. They can just go from there. And most software packages, when you plug the data into it and say, give me the p-score for this statistic, that's what it gives back. So it's driven actually more off of software than any statistical reason. So if you ever run an SAP program, or if you ever run, you guys ever, or ACAP, you guys have never heard of those software packages? Okay, well, SAP is what scientists use to do statistical analysis. ACAP is what hospitals use to do most statistical analysis. So you enter all the data into this software program, and it will compute a whole bunch of values. And one of the values it will compute is the p-score. And you need to know what that p-score means, because that's how you analyze whether or not you can accept or reject a null hypothesis. They're basically just, they're doing this. So if you put in a bunch of, so imagine if you will, you did this, right? So the idea is that you would go into the software and enter in the 100 scores. And it would tell you, after you enter in the 100 scores, oh, by the way, your p statistic, or your p-score, is 0.0228. And based on that, you can then write your conclusions, right? So if you were doing this for alpha equals 0.01, you cannot reject. If you were doing this for alpha equals 0.05, then actually you can reject, right? Because if alpha was 0.05, this number is less than it. You actually can, at a 0.05 level of significance, reject the null hypothesis. And again, this is another reason why you need to ask people when they're talking about statistical analysis what level of significance or what level of confidence they are running their data at. Because this answer changes based on what our level of significance is. If it's 0.01, we can't. If it's 0.05, we can. And it's purely up to you as to which one you think is correct. Welcome to statistics, folks. This is why it's half math and half social science. Because you can kind of say two totally opposite things from the exact same piece of data, right? With a level of significance of 0.01, we cannot reject. But with a level of significance of 0.05, we can. And that's just what the data says, okay? So, I mean, I don't want it to sound like we're being purposefully obtuse, but you can be if you want to. That's a good statistician knows that that's possible, all right? And this is oftentimes why you want to look at the person who's doing the statistical study and see, are they being paid to do this, and who's paying them to do it? Because if I wanted to reject this data, I could say, oh, I'm going to do my analysis at the 0.05 level so that I can reject. But if I'm paid by another group that says, well, I'm only going to pay you if you don't reject, I can do the exact same study and just change my level of significance to 0.01, and then I can say, oh, sorry, I cannot reject this data. And it's the same set of data. Welcome to statistics, okay? This is what makes it annoying and why people look at it and say, I don't believe it, it's not true. Well, it is true, it's just that you have to know enough to know when it is versus when it isn't, okay? So, it's one of those fuzzy parts to statistics that you just have to realize is there, all right? All right, so it's just a good problem to look at. All right, and note that I contrived this problem very specifically so that happened, okay, so that we can talk about it a little bit. All right, it's not always going to be this easy to have it be wishy-washy, but there are definitely times where it is, okay? All right, so let's actually pick a problem from 10.3 then and do it. All right. So let's do number 25. All right, so number 25 says, manufacturer needs to test that his bolts are 2 centimeters long when they come off an assembly line, okay? So he's running a big factory and he's cranking out bolts, as many as he can per minute or per hour, however it works. And he needs to recalibrate his machines if the bolts are too long or too short, all right? So, manufacturer wants the bolts equal to 2.0 centimeters long. He must recalibrate if too long or too short. Okay, so that sets up the problem that you're trying to test, all right? From this piece of information, you should be able to tell me what the ho and the ha are, all right?
O is equal to 2.
What?
O is equal to 2.
Ho, mu is equal to 2, not 0. 2,
And mu is equal, or not equal
perfect.
to 0. Or 2.
Mu is not equal to the other 0, 2.
Yeah, whatever the numbers are.
All right, so that sets us up for the mu, for our ho and ha. So now, we sample 100 bolts. X bar is 1.9. Okay, this looks familiar. And the standard deviation equals 0.5 centimeters.
So,
And we did something that was very similar. Note what we're using our level of alpha at this time, folks. 0.05. And note, what kind of a test is it? Two-tail, right? I made my first example one-tail because we had less than and greater than. Here it's not equal to and equal to, all right? But it's pretty darn close, all right? So again, you can think of this in one of two ways. You can think of this as reject if Z is greater than our C critical, or if P is less than alpha. And this is a good problem to work on because note, folks, one of the things that you have to do with your P-score is that when you are dealing with a two-tailed test, you must divide your P by a half in order to properly work with the both sides of the tail test, okay?
So if we do a P, we have to do a half.
Exactly. So note, when test is two-tailed, you must use P over 2 less than alpha to take into account both tails. Oh, and not P over alpha, not P over 2, 2 times P. My bad, sorry. Strike that, reverse it. All right, so let's look at it from both sides. Let's look at it from the Z critical side and from the P and alpha side, okay? So theoretically, folks, what is our Z critical value if we wanted to work with this? Our level of significance is 0.05, and this is a two-tailed test. So you can just read it straight off the table. .96. So, now what is our Z score? X bar minus mu all over S over the square root of n. What's X bar? 1.9 minus 2. Yeah. I mimicked my question off of theirs. Careful though. Technically. -2, technically, right? So again, remember that this remember it's two tails, so we can be greater than the z critical value or less than the negative z critical value. -2, folks. It is a little bit less than -1.96, so we actually can reject the null hypothesis.
Wait a second. Z greater than. Oh, okay, now.
Think of it as take the absolute value of z. If it's greater than the z critical value, then you get to reject. So 2 is just a little bit greater than 1.96. So this is going to be one where we can reject. Now, folks, what's the p-value for this particular sample? What was the p-score for 2.00? 0.0228 or something like that.
That was the negative.
Same thing, yeah. 8. And remember, what do we have to do with that number, technically? Times it by 2. P-score. Times 2. What's 0.0228 times 2? 0.0456. Is that number less than 0.05? Yes. Therefore, we can reject. Yeah, less than the alpha. If p is less than alpha, then we reject. If z is greater than z critical, if the absolute value is, then we reject. And so either one of them we look at is going to tell you reject the null hypothesis. Because p is less than alpha, we reject the null hypothesis and assume the alternative hypothesis is valid. So in general, that tends to be the way statisticians will determine whether or not you reject or accept a specific hypothesis by using p-scores. I'm indifferent as to which way you guys look at this. If you want to look at it as z to z critical, that's great. If you want to look at it p to alpha, that's great too. I will be happy either way. Just make sure that you do the correct thing. Either reject the null or do not reject the null correctly. All right. Not bad? Note, folks, that some of those questions on the homework are meant for you to just do some lookups, and based on the lookup, determine whether or not you reject or accept or not reject. Again, don't overthink some of the earlier problems and try and do stuff with them. They're more look up the table and then answer the question. Right? So not until you get to the word problems do you have to do this kind of analysis where you actually calculate the z-score and then look up the p-score, et cetera, et cetera. All right? All right. That's 10.3. So we've looked at small proportion size, we've looked at large proportion size. If you go back to chapter 8 and chapter 9, what did we do after large and small?
Yes.
Proportions. yeah, there were some weird ones in there with dependencies, but. 10.4 is testing whether a proportion is actually going to be more or less or equal to a specific value. Same sort of stuff that we were working with before, just now we're going to be dealing with p's and p hats instead of mu's and x bars, okay? Blah, blah, blah. Okay, we will be using p and p hat instead of mu and x bar. And if you think back to the chapter 8 and chapter 9 things, life is very much so similar. When we dealt with proportions, remember that we always dealt with z-scores. And so in general, when we look at 10.4, we are going to calculate a z-score, and that from that z-score, calculate a p-statistic, and play that game we just played a little bit ago. All right? And the z-score calculation is going to look very similar to what we've dealt with before. Please note again that p hat is the sample proportion. And p is your ho or your ha proportion, right?
Which one did you want, ho or ha?
What do you mean?
So the testing portion, so that's the ha.
Remember that it's always in both, right? Because it's going to be p is equal to that percentage, or then it's going to be not equal to that percentage. Or it's going to be more than that percentage and then less than that percentage. So the number will be the same in both the ho and the ha. All right? Note, folks. Standard rules from chapters 8, 9, and 7 and 6. Make sure you test that first. If n times p or n times 1 minus p is not greater than 5, all of our statistics break down. Okay? Right, so basically the law of large numbers is in effect, and you have to have enough numbers such that the probability is going to be at least more than 5 when you multiply it out. All right? Otherwise, the statistics break down. If either is not true, you cannot do any statistical testing. Okay? So the same rules that we had with before, they're still applying now. All right?
Like the Dragon Rider thing, where as you talk, it just, it's not.
I don't talk clearly enough.
Yeah, I think we'd have too many jokes. And laugh.
And there's too many cuss words up there too. That would be bad.
Ross just reviewed. What the hell is he teaching?
All right, so shall we do one? All right, let's suppose. Let's make one up. All right, so let's suppose I believe that my pass rate in my college math class is 70%. Points up. It's way higher than the national average if it is. National average for the national average of students passing a college math class is somewhere right around 48 to 52%. Usually it's about half.
You're talking about the college math or college math in general?
The college math style class taught at all colleges in this country, pass rate's usually somewhere between 50 and 60%. Yeah. All right, so if I say that my pass rate's 70%, I'm actually being too nice. All right. So honestly, I would. All right. So last semester, I taught. Let's say I taught 60 students. And let's say that should I be good or bad? Bad. Okay. So that's 60 students and 40 passed. Test that my pass rate is less than 70% at alpha equals the 0.05 level of significance. So, in theory, if I was going to make this claim that I passed 70% of my students, and this is the data I gathered, could someone tell me that I am a liar? All right, so what are we going to do first?
So P-hat is the 60 students. That's your sample population.
That's n.
Oh. Then the 40 is that.
40 is the number that passed. That's the x. Right? So p hat's always x over n, right? But start with, what's my ho and ha?
The 70% is the ho, and it's the.
What am I trying to test?
So your ho is p greater than or equal to
Uh-huh. The ho is that p is greater than or equal to 0.7 because what am I testing in the ha?
being less than.
Yeah, uh-huh. So what I really want to test is to see if I'm less than that 70%. Someone really, really, really wants to call me a liar, right? And so they're doing a statistical analysis to prove that I really am a liar. Very common sort of thing to do with government employees. Grab some data, in theory, and then use it, right? All right, so first thing you got to do is tell me what p hat is.
4 over 6.
X over n, 40 over 60. Let's round it to hundredths just to make it easy.
Minus the 0.7.
0.67 minus the 0.7 divided by 0.7
times 1 minus 0.7
times 1 minus 0.7
divided by the 60.
divided by the 60, the number of students that I actually had in class. Here's your z-score. Note it's negative, right? Because 0.67 minus 0.7 is negative 0.03.
-0.9.
0.9, yeah. Oh, all right. What am I going to round that to, folks? This is approximately negative 0.51 because we're going to look this z-score up in the p-tables, right? To figure out what our p-score is, right? So what is my p-score? So look up negative 0.51 in the tables. Table A. 3050. Is my p-score less than my alpha?
Yes.
Is it less than 0.05? Definitely not, right? So what do I do? Exactly, right. Because my p-score is so large, we would say do not reject null hypothesis. In other words, I am not a liar, folks. I am vindicated. Thank you. But this is exactly the sort of stuff that I would use if someone was saying, you're too hard on your students, you don't pass them enough, right? I could say, here's my data, doing a statistical test to show that I am passing 70% or more. I cannot reject that, therefore it is assumed okay. That's really a bad assumption, but it's all right because it's statistical. True. As long as there's data, folks, you can say whatever you want. The data doesn't have to be real, right? You can just make it up as you go. I swear, this was a random sample. All right, not too bad though? All right, so let's do one from the book so that we can crank through one of these.
4, 6, 8, 10. Wait, no, the following.
What did I assign in 10.4?
4, 6, 8, 10.
4, 4, 6, 8, and 10? Oh, because there's not that many problems. Well, what a bummer. All right, so let's try and do, oh, that first one's crap. Even the second one's crap. Wow, these are all crap in my opinion. Bleh. All right, well, let's go ahead and do then, which one would you rather do? Would you rather do the,
Which one has the most work?
yeah, the apnea one's got lots of words. Let's not do that one. Okay, so let's do number 7. Talking about the National Center for Health Statistics. Says that 75% of American women have been married by the age of 30. So Patrice, a single woman of 32 who has never been married, claims that this percentage is way too high. So she wants to do some statistics to prove or disprove that, right? All right, so NCHS says 75% of women are married by age 30. Patrice wants to test and claim that it's less than this. Test that this percentage is too high. At, what was our level of significance? Alpha equals 0.10. All right, so what's our ho and our ha, folks?
When the less than, so it's gonna be,
Yeah, that's
Less.
0.75.
where,
Where's that go?
so say greater than on the top,
Uh-huh.
7.7, and less than.
On the bottom. Right? We want to test that it's less than. And what she really wants is obviously that it is less than 0.75. So that's what we're trying to get. Now, what does our data say? Test the claim. She surveys 125 women. N is 125. 92 of them are married. X equals 92. Does this work? No, technically it's just straight X. X bar should be an average all the time. Okay. So, folks, what's P hat? 92 over 125. Somebody punch that out really fast.
Somebody up in Ross said it.
What was that? 0.74. We're gonna round, yeah. Not boding well for Patrice here, folks. All right, so what's gonna be my z-score, folks?
You have to use that.
0.74 minus 0.75 all over the square root of 0.75 times 1 minus 0.75 all over 125. I doubt that's going to be a very high number. Zero one divided by the square root of 0.75 times 0.25 divided by 125. Huh, that's weird.
What did you get?
I got 0.25819888 blah 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 blah.
Negative.
Negative, right? Blah, 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 blah. Since this is a z-score, folks, where are we going to round it to? Hundredths. And look up in your tables, what's the p-score for this z-value? 0.3974. Is it less than our alpha?
No.
Do not reject the null hypothesis, and potentially the National Center for Health Sciences is correct that 75% of women are married by the age of 30. You kind of hope they would be right. Again, though, nowadays, who knows? All right. Not bad, though? Folks, that's all I wanted to get through today. So I am more than welcome to kick it off a little bit early today. Please note, folks, if you could get through the first 4 sections of Chapter 10's homework, if at all possible. it shouldn't be too terribly bad, I hope. What was that, Haley?
Stuff on Blackboard.
Scans posted on Blackboard?
Oh, no, not yet. I'll do that I'll do that after class. If you have your chapter 9 and or 8 homework, I would love to have it, of course. The sooner the better. Please don't wait too long or I'll start to get pissy. I think I did, yeah.
I unfortunately got a little distracted last weekend. Finally locked in my day, or finally picked out and locked in my day for my tryouts. So.
Okay, cool.
Actually, to be technical, I locked it in today when I first got to school. Got my email back. They're like, "Yep, we reserved your spot for your tryout."
Cool. Do you know what you have to do?
Well, it's going to be a non-contact, and so far the non-contact.
So it's all gonna be like speed and strength.
Speed, strength, yep. Vertical, distance jump. So pretty much everything I gotta get. Somebody was saying like, man, if you go to one of these tryouts, make sure as a DN, which I am, they're like, make sure your hands are fast. So I'm gonna have to start some sort of boxing, something to get my hands quicker because
Yeah, true.
my shoulders are still kind of an issue. So if they're
Yeah.
putting maybe, I don't know, dummy hands to just see if I know how to rip through an offensive lineman fast or what they're doing, I don't know.
Right.
He could have also been at contact ones where you're actually going one-on-ones with defensive linemen versus offensive linemen, no pads,
Right.
which is pretty much hand and footwork.
Right.
So, I'll get there.
Alright.
If not, this is just going to be the first one this year.
Are there a bunch that you can go to and stuff? I mean, do you,
Throughout the year, they have camps. Yeah, I mean they had all their like late winter, early spring dates up, like about a month ago, and now just like within the past few weeks, they put all their early spring, late spring, early summer ones.
Alright. And is it team driven or is it association driven? In other words, is it
Team.
so each team has a different.
Yep, they have different ones across the United States.
Alright.
You got email and sign up for. The hardest part was getting my damn passport last weekend. God. The hard part is saying bye to my money because I'm already so low. I'm gonna have like $200 within the next couple weeks, and it's the beginning of the month. I've already paid all my bills
Oh.
except for my girlfriend's promise ring that she wanted for Christmas. So I just have that $30 payment, and then it's mainly affording food.
Yeah, I mean that's not trivial for trying to keep weight on and et cetera, et cetera.
Yeah. Oh, I'm starving right now. But unfortunately, I would go down to the cafeteria, but I would, or I'm waiting for my girlfriend.
Cafeteria's not open anymore, is it?
What's up?
Cafeteria's not even open anymore, is it?
Maybe not things off the line,
True.
but I could still get like a burger.
Oh, this.